Thank you very much. So I'm afraid I cannot say any more Chinese than ni hao, so I will have to speak in English. Try to speak slowly, hope you can understand. And I hope you can hear me. I will try to stand here instead of using the microphone if this remote will work. So I'm working with liquid crystals. I'm coming from a liquid crystal background, and since a couple of years I'm exploring the combination of liquid crystals with various other materials and other techniques. We're working with microfluidics, we're working with electrospinning, and we're applying liquid crystals in robotics, in security, and also in functional responsive textiles. And the latter, this topic is what I will be speaking about today, how we can functionalize fibers, not yet textile fibers. We are moving towards textile polymers. The aim is to do textile fibers that are functionalized with liquid crystal inside, and then use these textiles for gas sensing in particular. That's what we have been focusing on. So what I would like to do today is to first of all tell you about what you are seeing in the background. That's a liquid crystal floating on glycerol, and you see that it's changing, and that's because this is a soft material that is very responsive. Very briefly, I will just give you the key ideas of what we mean with liquid crystal. And then I will say a little bit about the motivation for this study, where we are targeting wearable technology, and give you an idea of where we want to be going. And then I'll tell you about how we make liquid crystal functionalized fibers by means of electrospinning, and in particular coaxial electrospinning. And finally, I'll show a little bit what we can do with the fibers we have in terms of gas sensing. That is where we have advanced the most at the moment. But before I tell you about the research, I thought that you probably don't know very much about Luxembourg. So I thought I'll tell you just a few words about the university I'm working at. This is a picture from the new campus in Luxembourg, and it's very close to the border of France. And it's actually interesting for Chinese to know that Luxembourg is famous as a very rich country. It has one of the largest GDPs in the world. And it was a very poor country until around the 1950s. And the wealth came from steel. Luxembourg became a very, very important steel producer, and believe it or not, there was a time when Luxembourg produced more steel than China. And it's incredible to think of, considering the sizes of the countries. So it was very successful for some time, but then China and other Asian countries really took over, became very successful and dominated, and steel production in Luxembourg went down. And then came the banks. And today, Luxembourg is very much famous for banking. And now also banking has more difficulties for various reasons. And so the government wants to diversify the economy in Luxembourg, and that's why they invested in starting a university. But I'm telling the story of the steel industry not only because of the link to China, but also because if you look at this campus, you see the new buildings here, and these are university buildings, but you see there's something in the background that doesn't look like university. These are the old steel, this is the steel foundry that is not in use anymore, but it's kept as a kind of museum component. So the new university campus is actually built where the steel used to be produced in Luxembourg. And that's the link a little bit to the history. So where is Luxembourg? It's actually pretty much in the middle of Europe. I don't know how many of you have been to Europe, but you probably heard of France, Germany, England. And Luxembourg is this tiny, tiny country here between Belgium, Germany, and France. Those three countries border Luxembourg. And it is so small, actually, that if I leave my home in Luxembourg City to go buying furniture at a big department furniture store called IKEA, I have to cross the border to Belgium. And if I take a walk from the new campus, I can walk across to the border to France. So you are it's a very mixed country where you hear German, French, Luxembourgish, of course, Flemish, even Chinese, Japanese, Korean, English being spoken. You have a lot of European and international presence in Luxembourg. The university, as I mentioned, is very young. It was founded only 15 years ago. And as you can see, it's very small. We have only a little bit more than 6,000 students. But it has been quite successful in generating good research and hiring good researchers. So the strategy has been to focus on research, to make the university, to give the university a presence and a bit of reputation, and then hopefully to get more students. So this has paid off fairly well in the university, in the Times Higher Education University rankings. We are presently number 179 in the world. And there is a category for young universities, meaning universities younger than 50 years of age, and we are number 11 in that. So that's a little bit introducing the university where I'm working. This is my group, the Experimental Soft Matter Physics group. As you can see, we were lucky to have some snow falling when we took this photo, so we went out and got the group photo taken. Luxembourg usually has some snow every winter, but not that much. It's actually, the climate is not the best. We have a lot of rain, but it's okay. And every now and then we have a nice day like this. The person who has done most of the work that I'm speaking about today is Catherine. Catherine is from the United States, and she is getting close to finishing her PhD. She's writing her thesis right now. And her topic is electrospinning and liquid crystal functionalization of fibers. But overall, we work with a couple of different topics, as I mentioned in the beginning, and I'm not going to tell you about all we do, but if you're interested, you can go to our website, which is this www.lcsoftmatter.com, and there you can find this subway map, and you can click on the different topics, and you see that everything we do is kind of focused on self-assembly and soft matter. But then we go in different directions. Liquid crystal is an important branch. Liquid metals, we do a little bit on stretchable conductors. We do a lot on electrospinning, on microfluidics, polymerization, colloids, and so on. Okay, so for those of you who don't know liquid crystals, what are they? Before I tell you what they are, maybe I say a few words about where you find them. How many of you have a liquid crystal at the moment in your possession? What do you think? Hand up if you own a liquid crystal. Nobody? So hand up if you don't own a liquid crystal. So this time you are right, because everyone today owns a liquid crystal. So almost every display, like this one, watch displays, mobile phone displays, they are using liquid crystals. But even more, you are liquid crystals. Your cell membrane are in a liquid crystalline state. So liquid crystals are actually quite important, both for life and for applications. So liquid crystals suggests that these are materials that are somehow between the liquid state, and liquid means it flows like water, but liquids are usually isotropic, they are disordered, and that's where there's a big difference to crystals, which are solid and they are ordered, and that means that they are anisotropic. They have different properties in different directions. And you can recognize isotropic from anisotropic by looking at them between what is called crossed polarizers. And every display, like this one, has crossed polarizers. When you go to the 3D cinema, you're wearing glasses with polarizers. So polarizers are actually used a lot. And to give you an idea of what we're talking about here, I just remind you, I hope you have seen this in high school physics. What is light? Light is it's a wave, an electric field and a magnetic field that are oscillating perpendicular to each other. And the polarization, what we mean with the polarization is in which direction is the electric field oscillating. And the light from the sun or from these lamps, that's unpolarized. So you don't know in which direction the electric field is oscillating. It can be in any direction. So what we do is we send it through a filter that is called a polarizer, and that lets through only one polarization. So now we have determined that the electric field will be oscillating in one particular direction. And if you then take another polarizer, but you rotate this 90 degrees, then you know that the first one will only let through this oscillation, but the second one will block that. So it's going to be black where they overlap. Except if you put a material between the two that changes the polarization state. So it can change the oscillation direction, or it can even induce a circular polarization or something like that. These materials are called birefringent, and they are anisotropic. So you can always recognize an anisotropic material by the fact that you see colors between cross polarizers, whereas an isotropic material like water will not do that. So if you now go back to our little comparison and you look at what does a liquid crystal look like between cross polarizers, it looks like this. So you see you have a lot of colors, but you also see that it moves. So here there's a glass cover slip, and I'm touching that very, very gently with the spatula, and you see that it flows very easily. So it's really a liquid, but you see colors, and those colors tells you that this is an ordered, long-range ordered liquid. It's anisotropic, it's birefringent. And that's a bit weird in a way, because anisotropy and long-range order usually comes with a lattice that you have in a crystal, in a solid crystal. So how do you get this in a liquid? Well, you need to have the anisotropy on the molecular scale. Each individual molecule has to be anisotropic. Anisotropic means not like a sphere. One direction has to be different from the others. So for instance, an ellipsoid, a rod, is anisotropic. And what is particular about liquid crystals is that these rods, they tend to order up in roughly the same direction, spontaneously. And that's what defines this special direction, the anisotropy, and gives rise to the birefringent properties. And if you compare to solid crystals, I don't know how many of you have some background in solid state physics, but if, for instance, in electronics, there's a lot of work today in wearable electronics, e-textiles and so on. And one of the big problems is that when you want to make something flexible and stretchable in electronics, the problem is that it breaks. So you use twist and stretch, and solids, they tend to break after a while, and then they lose their properties. And that's because they have a lattice, you have domain boundaries, and so on. They are brittle in this sense. The nice thing with the liquid crystal is that there is no lattice, there are no grain boundaries. You can twist, you can stretch, you can bend. You're not destroying anything. It just comes back to, it just adapts to whatever situation you do. So this type of liquid crystal, where you have just uniaxial, one-directional order, we call that pneumatic. And I'm going to talk about that one, but also about a special version of which is called chiral pneumatic. Chirality means a lack of mirror symmetry. It comes from the Greek word for hands. You know, your right hand is different from your left hand. You superimpose them and they're different objects. So chirality means that you break the mirror symmetry. And a screw, for instance, is chiral. A right-handed screw is not the same as a left-handed screw. And you add a chiral molecule to a pneumatic, and you get this type of spiral deformation of the director field. And the reason that's interesting is that this means that you get a periodic structure, right? If you go up a spiral staircase, you go up one turn and you come back to where you were, but you're higher up. So it's a period. And this means that when you have a cholesteric liquid or a chiral pneumatic liquid crystal, it's also called cholesteric, that means that you have a period because of this spiral staircase-like structure. And any periodic medium will interact with light if the period is similar to the wavelength of the light. And that is exactly what we can do with these types of liquid crystals. The period, the pitch, can be on the order of a few hundred nanometers, and then you get selective reflection of light. So this is actually a flat cell of a cholesteric liquid crystal that when you look at it straight on like this, it looks red. But you see when I tilt it, it's exactly the same cell. The color changes from green to blue. And that is because this color is not like the pigments in our clothing. It's structural color. You also find it in nature, in peacock feathers, in abalone shells, in a lot of bird beaks, parrot beaks, and so on. And that's always because of the structure that is periodic, and it interacts with light, so it reflects a certain wavelength, but that wavelength depends on the angle. So you change the angle, and you change the color. Moreover, with liquid crystals, the pitch is also temperature dependent. So in this case, we have a temperature gradient. This is cold, this is hot, and you see the reflected color changes from infrared, we don't see it, to red, to orange, to green, to blue. And it can also go to the UV. And that means that you have a temperature sensor by just looking at the color. So that's quite useful in sensing, obviously. But there are many other ways that you can use liquid crystals for sensing. And what you're seeing here in the background is a phase transition from the isotropic non-liquid crystalline liquid to a cholesteric liquid crystal. And you see that it goes from black to colored, and then the color changes, and it goes back and forth, and you see a lot of patterns and so on. And that is because you have this change in order. And you can have a lot of different phase transitions. So we speak of the melting point. That's a classic melting, like ice melts to water. That's when the solid melts to liquid crystal. But then you have a special transition temperature, and that's when the liquid crystal phase disappears, and you get a regular isotropic liquid. And the regular isotropic liquid looks clear, looks like transparent, like a glass window, whereas a disordered liquid crystal doesn't. So it looks scattering. So we call this the clearing point. And the interesting thing is that you can induce these phase transitions. In this case, we're heating. That's what you often do. You induce a phase transition by heating, like you boil water or you melt ice. But you can induce them with light. You can induce them with gas exposure. You can induce them with various contaminants and so on. And this can all be used for sensing. That's why it's quite interesting in that context. Okay, so let me start speaking a little bit about what we do with liquid crystals inside fibers and how we do them and why we do it. So the motivation is to kind of develop a class of wearable technology that doesn't quite exist today. So wearable technology is a very fashionable term. We all probably heard of devices like the Apple Watch and the Samsung Gear and many others. But the interesting thing is that we think of these as very modern devices, something completely new, but fundamentally, watches have been around for ages. Where, if you think about it, Middle Ages, what were the soldiers wearing? Armor. Very rudimentary, but very, very simple wearable technology in some sense, right? And soldiers today, of course, wear a lot of technology on them. So wearable technology has been around for quite a while. And what I think is really interesting is that it's not just bringing technology into something wearable, but rather making what we wear anyway, our textile clothing, making them responsive and functional. And it's not only me who says this, but the industry is recognizing this as well. This is an article from 2015 in Wired, where they focus on this, that this hype about wearables, being watches and wearable computers and so on, that's not really so interesting. The really interesting thing will be when our clothing becomes smart and useful. So many companies like Nike, Ralph Lauren and so on, they're really interested in taking that step. But it's a big step. We're not there yet, definitely. So if you think about wearable technology in that context, that making our clothing intelligent, or that's a bad term, but responsive, let's say, functional, then you have to think about what is clothing like. Well, first of all, we move, we bend and we stretch and we jump and so on. So the clothing has to support that. So it has to be flexing, it has to survive flexing and stretching, bending and so on. And of course, it's very important for our comfort that the material is breathable, that we can get water out and air in, and otherwise it's very uncomfortable. So we really want to have textiles, but if you look at a lot of research today on wearable technology, you will see that a lot of them work on, for instance, putting electronics on a PDMS sheet. And PDMS is rubber. How many of you today are wearing rubber? I think this is correct as well. Nobody. Unless you're a diver, or you have some very kinky ideas, you probably don't wear rubber. It's very, very uncomfortable because it's not breathable. Another thing that is maybe not as obvious is we also don't want our clothes to catch fire or explode. And until the Samsung Galaxy, was it S8 or S9? I don't remember now anymore. There was this model of Samsung Galaxy that was forbidden on airplanes. That became a big thing. People realized just how dangerous a mobile phone is actually because of the battery. And a colleague of mine, he told me that the power stored in a mobile phone, that compares to a hand grenade. And if you think about that, that's pretty astonishing and scary to some extent, right? So if you don't control the energy that is stored in a mobile phone battery, you can have very, very bad accidents. Now, mobile phones is one thing, but what if you distribute batteries in your clothing and that battery catches fire? That's going to be a very, very unpleasant experience, right? So in principle, I would say it's very good if we can avoid distributed batteries. So our vision in our research is really to make the fiber itself functional and incorporate the responsive material really inside the fiber and avoid electronics whenever possible. Of course, it's not always possible. Sometimes we really need electronics, sometimes we really want electronics, but we don't always need electronics. And sometimes it's quite useful. So what you're seeing here is one fiber that contains this cholesteric liquid crystal that gives a blue color because of the structure that it has, this periodic structure. And we're heating it past the phase transition from cholesteric liquid crystal to isotropic liquid crystal. And then the structure disappears, it becomes disordered, and so it cannot reflect one color anymore, and that's why the color disappears. So you can have a color-changing textile in principle. So we work with electrospinning, and let me say straight away that I'm not saying that electrospinning is the way forward to make smart textiles or clothing. For us, it's a very convenient research method because it's a small-scale lab equipment that we can easily change parameters of and do research really. I think once we figure out the basics, then the next step will be to switch to conventional spinning mechanisms, but transfer the knowledge that we have learned from electrospinning. But for us, this is an interesting approach. So maybe many of you know about electrospinning, but if someone doesn't, I include this anyway. So in contrast to standard spinning techniques, we are not driving the spinning with pressure. We are just pumping the solution very slowly to the spinneret just in order to replenish it. What we're doing here is that we are acting on the ions, the charges that are always present. And we're applying an electric field that is pretty strong, a couple of kilovolts. And that tends to separate the ions. And the ions, one species of ions wants to go to the ground, the other wants to go to the spinneret. But surface tension of the liquid wants to keep a sphere. It doesn't want this pointed shape. So you have a conflict that is called the Taylor cone. But eventually, the electric field wins, and from this Taylor cone, you get a thin thread or thin jet ejected that becomes a fiber once the solvent is evaporated. Our specialty is we work with coaxial electrospinning. So inside the main spinneret, we insert a second, thinner capillary in which we can pump the liquid crystal or pretty much any other liquid that is compatible with this. And then we get a core sheath fiber where the liquid crystal is surrounded by a polymer sheath. And this is what it looks like if you look at the beginning of the spinning process. So this here, you see the droplet, the internal droplet, that's the liquid crystal. And the outside droplet, that's the polymer solution. And Catherine is slowly increasing the electric field here. So in the beginning, it's just dripping. But as the electric field is strong enough, you see the jet being ejected, and the liquid crystal is really inside the polymer solution. You can do this also with two capillaries. So here we use this was Yu Mikie, a Korean student who did this a little earlier. And this here is a glass capillary with a theta-shaped cross-section, so it has two compartments. And in those we put one capillary in each point. And you see one has been dyed with a black dye, and the other one wasn't dyed. And you see that they actually are separated, and they are spun out separately. And finally, if you look at the SEM of the fiber, you see that you get two separated channels in the final fiber. So you can spin multifunctional fibers in this way. The final fibers, if you look at them in the light microscope, this is polarizing microscopy between cross polarizers to highlight the liquid crystal. You can get them more or less continuously filled like this one, or sometimes you get them filled in little droplets. So depending on how you tune your liquids, you can get breakup into droplets. If you do focused ion beam milling on such a fiber, you can cut out a part of the polymer, and then you can really visualize the core where the liquid crystal was. With SEM, we can also see that the sheath, the polymer that surrounds the liquid crystal, can have very different characteristics. And in particular for this, for our purpose here, it's quite interesting that it can be made very porous. And that's of course interesting if you want to do gas sensing, because then the gas can easily access the core. Electrospinning, for those who have done it, you probably know that it's very, very sensitive to the parameters of spinning. So for instance, humidity is a critical issue. So almost every lab that does electrospinning, they prefer to work in the winter, because in the summer it gets humid and nothing works anymore. And this is an example of the enormous difference you can have. This is exactly the same liquid crystal polymer combination that we spin with the same parameters, except the relative humidity is 25% here, and you see you get nicely continuously filled cylindrical fibers, whereas with 61% relative humidity you get this beading and not complete breakup, but very non-uniform fibers. Interestingly, both of these are interesting. It's not that this is useless. This is what we usually are aiming for, but this turns out to be quite interesting as well. And just to illustrate what we can do microscopically, as I mentioned, these cholesterics or chiral pneumatics, they show the structure and color. So if we spin fibers of spin a mat of fibers with a blue reflecting cholesteric, it can look like this. This is a macroscopic mat. This is a microscope slide. So it's about, I think it's about 3 centimeters in width and maybe 7 or 8 in length. And you see a distinct blue color when we look at it at room temperature, and you heat it up to 40 degrees Celsius and the color disappears. So basically we have a temperature sensing textile mat or it would be a textile if this were a different polymer. Right now it's polyvinyl pyrrolidone, which is certainly not a proper textile polymer. So what can we do with this? Well, we can do sensing, as I mentioned, temperature sensing. And now, so far everything worked fine, but now let's see. There we go. So this could be interesting in some contexts to have temperature sensing in the fiber. Okay, it actually is working. It can be used, for instance, for checking the temperature of fluids that are flowing in pipes. That could be quite interesting. But what we were particularly interested in is gas sensing. And this is an example. This is not fibers. It's a colleague of ours in the Netherlands who demonstrated that you can use cholesteric liquid crystal as a it's still working, yeah. As a means of testing for oxygen or carbon dioxide exposure, which is quite interested in food protection. So we're thinking of using this type of gas sensing based on, but putting them into fibers. So this is one of the first examples we did. This is when I was at Seoul National University in South Korea. We spun a fiber mat with a pneumatic liquid crystal inside, and you see it's covering the university logo, and we're exposing this to toluene vapor, and you see that the transparency of the fiber is changing. So, and this is just by the naked eye, you see this response. So that made us think that you could actually make a wearable gas sensor that you can incorporate in a uniform, for instance, for a factory worker, and the idea would then be that if there is a gas leakage, or of course for soldiers during a warfare situation, they would be immediately alerted by something in the atmosphere that is not very healthy. And it turns out that when you look at the fibers, that when we were trying to repeat this, we found that sometimes it worked and sometimes it didn't. And what happened was that the fibers that showed this type of very strong naked to the naked eye response, they were these beaded fibers. So that's why I mentioned that the humidity can even be an advantage sometimes, but you can also get the beaded fibers by just increasing the flow rate of the liquid crystal actually. But it turns out that this type of structure is good for seeing this macroscopic response, whereas these other smooth fibers, they give a slightly different response that I will show in a moment. So this is an example of what these beaded fibers look like at a more close-up. And this is an example of what the cylindrical ones look like. Now the interesting thing is that the beaded fibers, they are nice because you see the response with the naked eye, but these cylindrical ones are also interesting because they, even though you don't see the response with the naked eye, if you add cross polarizers, then you also see a response, and this is different and is very fast and sensitive, as you can see in this demonstration. So here the fibers are kept between cross polarizers, and you see that as soon as Catherine approaches with the toluene vapor, you immediately see a very strong response, and it also goes back very quickly. So this is actually quite sensitive and fast, which we think is interesting. And just as a control, this is the same type of fiber but without the liquid crystal, and nothing happens. So you definitely need the liquid crystal in the core to see this effect. Okay, I think I skipped this slide, but let me just, our next step is then to try to get quantitative data for how sensitive can we actually go. And this is not completely easy for this type of experiment. So what Catherine did here is that she set up a setup where she has a special gas sensing cell. This is a stainless steel chamber, and she connects it to a huge syringe. It's a 1 liter syringe. And the reason that she's using this is that it's a good way of preparing toluene vapor with controlled concentration is you simply take a large volume of air, you take an epilogue pipette and you dispense like a microliter of toluene, you close the syringe and you let the toluene evaporate. And then you know how much toluene you have in the air. Now, as I will tell you in a moment, it turned out that it wasn't quite as good as we hoped, because this syringe here, it's polycarbonate. These 1 liter syringes don't exist in glass. They exist only in polymer, and that turns out to be a problem. I'll come back to that in a moment. So we give the units in micromolar. So for those of you, or if anyone is interested in sensing, you will probably know that often thresholds are given in ppm, parts per million. That's a very tricky unit because there are different schools of how to interpret this. So much more straightforward is to simply give micromolar. So how many moles of evaporated toluene in a liter of air? That's what we were doing. And then, so what Catherine did is she prepares the fibers and she looks in cross polarizers with a green filter to give a more uniform result. And then she looks at how the transmission, how the intensity changes as a function of time. This is time. And you see that as a function of the concentration, 140 micromolar, well, let's say 500 micromolar or 800 micromolar, you see that she barely gets a response here, she gets a more distinct response here, and she gets a quite distinct response at that concentration. These are some technical details that maybe I will not go into. And what is more interesting is this one. So if you want to do gas sensing or sensing of toxic gases, of course it's important that your detection threshold is in the range that you detect something before you die, right? Before you are hurt. So this is the Osha Index. So this is an American institution that provides detection limits that are for safe exposure. So within 10 minutes, you should not be exposed to more than 500 ppm of toluene, which translates to 21 micromolar. And you see that our threshold, our levels are much, much higher than that. So it would seem that our sensors are totally useless. However, there are a few issues here that one must take into account. First of all, these values are probably wrong. They are definitely higher than the real value. And the reason is this syringe that I showed before. Remember, this was polycarbonate. And what we realized afterwards is that when you look at the data sheet, they say toluene is not a solvent that you can use with this syringe. And the reason is that the toluene is actually, it goes into the polymer. And we noticed this after a while, the syringe was starting to break and change character and so on. So when Catherine prepared the mixture of toluene air, actually a lot of the toluene stays in the polymer. And that means that the actual concentration level is much higher, much lower than these numbers. The other issue is that these data are averages, and if you look at individual points in the fibers, some points respond very quickly at very low thresholds, and some points respond much later. And we need to figure out why some points respond so much faster than others, and then we can probably get that threshold down very much. So these are some of the issues that we are working on investigating. In particular, defects in the cores are quite important. As I mentioned, some points really respond much faster than others. But let me just consider why would this be interesting in general? Because there are many types of gas sensors. Why are these interesting? Well, first of all, a lot of gas sensors work at very high temperature. Our sensors work at room temperature. Second, this is completely non-electronic. We don't need any power supply, we don't need any battery, we don't need any generator or anything like that. Especially if you can do this without the polarizer, it's very easy to see the response. It's reversible, and this is a low-cost, lightweight textile material that could be incorporated into uniforms, as I said. The big problems are really in terms of sensitivity and selectivity. We need to get the sensitivity down. I think that it is already better than what these first quantitative data suggest, but we still need to get better, and I think we can do it. And we need to get selective for certain VOCs, volatile organic compounds, in order that we get the response for only the one that we want to detect. And that's a challenge for sure. I'm not going to say anything about biosensing. And so let me summarize by saying that we can incorporate liquid crystals into fibers, and that opens many interesting possibilities for wearable technology, color-changing clothes, wearable sensors, and so on. And we have demonstrated gas sensing without any electronics working at room temperature. And I didn't go into it, but there is also potential for biosensing using these fibers. So I'll end with just an overview of some papers that we've published on the topic. If you're interested, you can find these, and I think they're all open access. And if you have any questions, I'd be more than happy to answer them. Thank you very much.